Another welcome, a warm welcome here from cold Germany. I'd like to officially start the third international conference here on SDB. It's a pleasure that you are here. I see actually a lot of attendees in the meeting. I expect others to come. We'll have a smooth start into the conference right now. So I would like to hand over to Edward Albada. Edward Albada is representing EOMAP in the North Americas and Caribbean region. Here he is. Edward is actually from Trinidad and Tobago, and his love to the sea actually made him study coastal oceanography engineering at the University of Florida. So he worked for over 25 years in the sector on coastal and planning projects, actually all around the globe. So he was introduced to satellite information, satellite-derived information and bathymetry almost six, 7 years ago, where he used this kind of data in various of his projects. So Edward would introduce you to the SDB Day, and without further ado, I would like to hand over to Edward. Edward, please.
Thank you very much, Knut. I'm very excited to officially kick off this this conference. So welcome to the third International Conference on Satellite-Derived Bathymetry. My name is Edward Albada, and as Knut said, I serve as principal for EOMAP's operations in the Americas and Caribbean region. I do have a very quick presentation to give, and it will not take too long before we get into the real presentations. But I'm excited to see all the participants in this conference, especially the students, who we expect, of course, to further the exciting field of SDB. And before we get started, some quick thank yous, of course, to our organizing committee, specifically Knut, who you just was introduced to, Christian Boedinger and Philip Klinger, who have really gone out of their way to make this SDB Day happen. Also, thank you to our presenters and, of course, our keynote speaker, Commander Waterson from the Australian Navy, and, of course, our moderator, Catherine Rice from the Deputy Director at NOAA's Office of Coastal Survey. So, very briefly, introduction to SDB for those who may not be aware. SDB is essentially measuring bathymetry from the reflection of sunlight off the seabed. It's a very passive system. It's particularly applicable for places which are shallow or unsafe or inaccessible to traditional survey methods. We do have some limitations. We're limited by the effects of either the depth or the turbidity, but it is applicable for a wide range of places around the globe. This slide demonstrates successful applications, that we've been successful with. Of course, places in the Caribbean with the clearer water, we have a very large range that we can measure, and this small slide at the bottom indicates the applicability in the Caribbean, but we're not limited to that. We can, as you can see in the globe, the picture of the globe, we can measure SDB throughout any regions of the globe, including the Arctic Circle of Canada. As SDB is experiencing accelerated uptake in the recent years, we decided that there was to be an established survey technology, and it's important that the users and providers worldwide have a venue for meeting, and we decided to establish this SDB Day to provide a venue for all of the experiences globally. And the first conference took place in the Lake District of Bavaria in Germany. It offered a very unique opportunity for users and providers to discuss the capabilities, data integration, requirements, and even quality standards. And then the next SDB Day was held on the Sunshine Coast in Malulula Beach in Australia. And the third, is the third SDB Day, It was originally intended to take place somewhere in the North American regions, but of course the COVID pandemic hit, and here we are in the virtual SDB conference. And although we miss out on the personal interaction and networking, we experience a much wider and international audience. So there are some benefits to taking it virtually. And so now I'd like to introduce our distinguished moderator, Catherine Rice. Catherine is finishing a 2-year term as the first female chair of the Mesoamerican Caribbean Sea Hydrographic Commission. It's a regional arm of the International Hydrographic Organization with 28 member states. The Commission works to ensure seamless regional electronic navigation chart coverage, increases capacity to provide the best quality navigational services, and advanced ocean mapping to inform the sustainable multi-use of the ocean. She also serves as Deputy Director of the NOAA Office of Coast Survey, is responsible for mapping and charting US coastal waters to meet the needs of the global mariners for a safe, efficient, and environmentally sound marine transportation system. We thank her for being with us today, and I now turn this over to her to introduce the rest of the session. Thank you very much.
Thank you very much, Edward, and a warm greeting as well to everyone, all the participants. Good morning, good afternoon, good evening, depending on where you are in the world. We're very glad to have you here, and we have a very interesting and thought-provoking agenda ahead of us. Just a few points of information before we go into the agenda. This webinar is being recorded, and all the presentations will be recorded and made available on the sdbday.org webpage after the event is over. We do ask that the participants put their questions and comments in the chat. We will take questions at the end of the session rather than after each individual presentation in the interest of time. So myself and others will be monitoring your questions in the chat, and after the presentations are concluded, then we will have some open discussion and allow responses to your questions. The speakers will speak for approximately 13 minutes. I will remind them gently if they are going over so that we will have that time for general discussion. So the agenda, it has 3 segments, and the first one is focused on the future of SDB developments and technologies, where we have a variety of speakers looking at these issues from different perspectives. Session 2 will be a hands-on workshop related to technology. And session 3 will focus on SDB standards and best practices for adopting SDB. So with that, I will move into introducing our keynote speaker. Was mentioned is Commander Chris Waterson of the Royal Australian Navy. He will be giving us his keynote via video. The time change challenges were just a little bit too much for him to be able to be with us personally. But he has worked with the Australian Navy since 2016, where he was awarded he's certified as a level 1 hydrographic surveyor, and he was responsible for planning and managing national hydrographic surveys. He helped to establish and implement Australia's National Civil Survey Scheme, the Hydro Scheme Industry Partnership Program, and was also his office's representative to the AusSeabed, the National Seabed Mapping Coordination Program. In 2019, he moved to the Maritime Geospatial Program within the Australian Hydrographic Office, where he oversaw the acquisition and introduction into service of the office's satellite-derived bathymetry capability. So with that, his video message can begin.
SDB is possibly the newest development in hydrographic surveying, and this is a very exciting time to be involved with this technology, as collectively We, as a community of SDB users, are shaping the future of this technology as we both learn and develop the technology, techniques and applications for SDB. Today, I want to share with you our SDB journey to look at what we have learned and to lay out some of the challenges we've faced in working with SDB. My journey began back in mid-2016 when discussion in defence, scientific and hydrographic circles about the advances in SDB generated sufficient interest for us to look further into the techniques and technology in this field. My first contact was a small meeting hosted by the Australian Hydrographic Office with industry, our national scientific and geospatial agencies to build our own understanding of both what SDB could do and the different offerings that were available on the market. Not long after this meeting, we received our first SDB software package and started separately purchasing processed SDB datasets under contract. Our initial experience with playing with SDB was a very steep learning curve. It wasn't just as simple as acquiring an image of a location and pressing start. Image quality, cloud, turbidity, satellite geometry all played a part and frustrated some of our early efforts. It became the case that we could spend days searching for a good image and only for a few hours of processing. We also learned that the results of an individual operator for a given scene could be vastly different from a second operator because they're using their own settings, adjustments and processing parameters. But again, we learned more as we progressed and by working with our partners, refined our own processes to improve the consistency and quality of our outputs. Now, I'm pretty sure some of us thought in those days that commercial acquisition of satellite-derived bathymetric data was much easier than doing the work for ourselves. But that was also a trigger for us. We liked what we thought could be done with the Watcor-X software package and decided that we wanted to have that package for ourselves so we could do our own SDB. After some commercial negotiation and a very lengthy government procurement process, we became the first organisation in the world to acquire a Watcor-X licence. Now, being the first customer for anything can go one of two ways, and I'm pleased to say that our experience has been positive. We worked very closely with EOMAP to ensure that the software package we were using worked the way we wanted. So even prior to delivery, we'd given a very lengthy wish list to EOMAP of the functions that we thought would be good in the software, and we were able to work together and bounce ideas off each other to help to find some new applications and ways to use this technology. Our initial focus for SDB was purely for defence planning. We saw SDB as a tool to process imagery and collect hydrographic data. But the more we played with the data and technology, we could see the potential for SDB in so many other ways. It grew from a straight data acquisition tool to a survey planning tool and a risk reduction tool. Not only that, the technology behind SDB helped us to automate other charting processes. Now, at this point, let me acknowledge the work of others who went before us in this field. Around the same time that we started actively using SDB, the UKHO had already published their first chart containing SDB as a source survey. This was particularly significant within the hydrographic world, as it demonstrated acceptance of this technology by possibly the most influential agency in our field and helped support our own case within my organisation to work with this technology. As hydrographic surveyors, we seek to prove the accuracy of any data collected, and hydrographic officers take a very conservative approach to publishing any survey data. So the fact that the UKHO had incorporated SDB into a chart was a major step to accepting this type of data within our own organisation. Possibly one of the biggest challenges has been the assessment and acceptance of the accuracy of SDB data. The horizontal accuracy of satellite positioning systems is widely accepted, so thankfully it doesn't take much discussion. The more challenging conversations have been held around the vertical accuracy or uncertainty of SDB data. In order to prove the accuracy of SDB for our own organisation, we ran numerous comparisons between SDB data against both LiDAR and multi-beam across a range of locations to prove the capability. We learned a lot from these comparisons, but significantly, we learned that where we had sufficient comparison or crossover data, we were able to tie the SDB to accepted depth information and improve the confidence and vertical accuracy of our data. As a broad generalisation, we describe SDB data as meeting IHO ZOC-C specifications, which are really quite generous. We view SDB as being around the 2 metre plus a percentage of water depth for vertical accuracy in the absence of supporting or comparative data. But where we have existing data in an area that can be compared against the SDB, we have the ability to refine the accuracy calculation and our own confidence in that assessment. And where the data supports this, we're comfortable that we can demonstrate accuracy supporting ZOC-B. I think it's also a significant advance that the most recent edition of the IHO Standards for Hydrographic Surveys publication S44 references SDB as a method for determining depth. This shows me that there's now growing acceptance globally of what SDB can offer. We've had to work hard within our organisation to build acceptance of the data and to educate users about the capabilities and also the limitations of SDB data, and we've had a few hurdles along this way. We've been using SDB as a survey planning tool to support our national survey program, and we've used this in a couple of ways. We initially saw SDB as an opportunity to reduce the risk of grounding for our survey ships, particularly if we could provide shape files or overlays for their navigation systems to help in the avoidance of dangers. Now, prior to every survey, we process the survey area with SDB at the planning stage to help in this risk reduction. But there was another factor to this. When we started looking at contracted surveys, we had to ensure that we were getting the best bang for buck for our survey dollars. This worked in a number of ways. First, we could identify the shallower parts of a prospective survey area. We were then able to focus our survey efforts on the parts that were navigationally significant, which helps us to reduce our costs. And secondly, it enabled us to make better, more refined a priori assessments of a survey area, which in turn helped to ensure that we were realising the best value in terms of survey line planning to most efficiently survey an area. To demonstrate the cost savings that SDB can achieve, I'll point to my own calculations for the entire coastline of Australia. If we were to look at mapping our entire EEZ, we estimate that there's in the order of 10.8 million survey line miles. Now, breaking that down further, in the 2 to 5 metre depth band, there's 1.6 million survey line miles and another 2.4 million survey line miles in the 5 to 15 metre depth band. If we could even cover just 1/4 of that shallow zone using SDB, based on the current going rates for physical survey data acquisition, we could save in the region of $1 billion on our own national survey program. When you take it from that perspective, the value proposition of SDB, whether commercially purchased data or the cost of a software license, when compared against survey line mile costs or the daily running costs of owning a survey fleet, becomes a very simple conversation. Now, as we started providing this data to our planning and contracting teams within the office, we occasionally hit some challenges. This was particularly the case in areas where we had overlapping survey data from a previous survey. And the survey planning team could see differences between the depth accuracy in SDB and what we'd processed from their data. This is particularly the case around reef edges or steep slopes. As we know, SDB is dependent on the water properties for a quality return, and uniquely the resolution of the image, which can lead to pronounced edge effects. When we're using lower resolution imagery, this can lead to an edge effect where the steep slope of the reef edge is exaggerated seawards, and in this case is predominantly essentially a horizontal positioning error in the SDB spot sounding. The quality of the SDB data will drop off significantly as water quality varies and the complexity of the seabed varies, but that will not be readily evident in the SDB data. SDB data with sparse coverage or on the edge of extinction depths should be treated with some caution. As we've collected and processed SDB data, we've provided this to our charting section in our office, but this has also had challenges for incorporating the data into our national deconflicted bathymetric database. Firstly, our data managers weren't prepared for handling SDB data and had to develop new procedures for prioritising and deconflicting data. One of the issues we discovered was that when we processed 10-metre resolution imagery into a 10-metre resolution bathymetric surface, it became confusing for our cartographers, as the 10-metre bathymetric surface appears visually very similar to a thinned-down, high-resolution multi-beam dataset. We eventually overcame this by rendering 10-metre imagery as a 1-metre surface, which then shows SDB as spot soundings within the database and helps our cartographers visualise the difference. The next issue we faced with SDB data in our system was that data managers were in some cases ignoring SDB data because the ZOC allocated to a specific data set was lower than the other data in that database. We've overcome this by revising our data deconfliction procedures. Now, as we started playing around with Watcor-X, one of the really clever guys that works in my team worked out that the land masking feature would work well as a coastlining or feature delineation tool. And after a bit of playing around and some script writing, he demonstrated that the land masking feature could indeed extract a coastline for a survey area and export that as a shapefile. To understand the significance of this functionality, it helps to consider how nautical charting has advanced over the last few decades. When I started navigating ships, we were still using paper charts, and GPS positioning was a relatively new technology. Charts were a combination of metric and fathoms charts and were often on different datums. As the world moved towards electronic charting and ENC started being released, there was a race by hydrographic offices around the world to convert all of their charts to metric and WGS84. The problem with this was the conversion process to fit the WGS84 datum was not always straightforward, and as a result, old coastline data was at times stretched or compressed to fit corresponding reference points. Further, much of the old coastline data, especially in remote areas, was based on sketch surveys. The result is in many cases, you would end up with features that were literally a mile out of position. So for a hydrographic office, understanding that some of the legacies that have carried over from older charts, we wanted to prove the assurance that there weren't any nasty surprises in critical navigation areas. In order for us to make this happen, we purchased some commercial SDB data sets in key shipping areas to confirm the positioning of features, which has given us the confidence to know that the dangers are actually where we say they are. But also it's come from challenges for our cartographers because they've had to work out how to manage shifting features that were potentially an old feature on an existing chart and making sure there wasn't a blank space left behind. Another area that we were naturally drawn to with SDB was the potential for SDB in humanitarian assistance and disaster relief. From a Defence Force perspective, we are often called upon to assist following natural disasters such as cyclones, and SDB seems like an obvious solution to find a way to navigate in remote areas to enable aid to reach those in need. My team did some really great work over the last few weeks helping to find access routes for our ships working around Heege to get them to where they were needed the most. Now, I've encountered the argument that immediately after an event, SDB will likely be of little use as the water quality will be too turbid or too rough, or there'll be too much cloud. And I agree there's the potential for that to happen. But in remote locations where you have sparse data, SDB from earlier imagery will help to identify likely landing locations, which means we can refine and focus our physical pre-landing survey areas and therefore reduce the time frame for us to start delivering help when it's needed the most. Remember that in this line of work there is no single solution, and SDB still has to be viewed as a complementary technology to traditional survey techniques. Also, if you consider the work that's just been completed in Heege, we were still providing SDB support 3 to 4 weeks after the event, meaning that the age of imagery was not an issue, particularly as time moved on after the event. As word has started to spread within our own Defence Force about the capabilities and possibilities of SDB, we've started to see an increasing number of requests for SDB from our fleet, including for applications we hadn't thought of. There are the requests you might expect for things like landing data for amphibious exercises, but we've also seen navigators asking for route assurance in remote and poorly surveyed areas. In the same way that we do risk reduction for our survey teams, we're now seeing risk reduction for remote area transits. We're also receiving numerous requests from our scientific agencies for high resolution data to aid in environmental modelling for things like wave prediction on beaches. Within our immediate region, I think that SDB has a bright future. The Indian Pacific region presents ideal conditions for SDB, particularly in terms of water quality and visibility. We've seen commercial surveys undertaken in the last few years that have shown the viability and effectiveness of SDB, particularly as a complementary technology to established physical survey methods. Within our own office, we've recently moved from a trial to full production capability that supports both our national charting and military functions. There's a large body of work ahead of us as we grow that capability and start to build our data through SDB. Moving forward, though, there are still opportunities for SDB to grow, and I pose the challenge to this audience. We're still challenged by surveying our polar regions, and SDB might offer potential solution to help to derive the answer, or even using another form of remote sensing technology. There's enough progress on drones and cameras that I think this might be the way to improve accuracy or resolution of the work happening with SDB. I also think that change detection will be another likely area for growth for SDB, particularly in coastal and environmental monitoring. From my few years of being involved with SDB, this has been an exciting time with numerous and rapid developments. When you consider the survey coverage that can be achieved by SDB and the relative cost involved, there is a very clear future for SDB, and I look forward to the advances that we will see in this field over the next few years.
Very interesting context-setting keynote speech from Commander Chris Waterson on the capabilities, possibilities, and challenges of SDB. So now we will move into our first speaker of the session, who is Dr. Thomas Heege. He is the CEO of EOMAP, which he founded in 2006. He has more than 25 years of experience in aquatic remote sensing research and applications. He develops international markets and growth based on satellite-based monitoring technologies for maritime industries and water-related governmental institutions worldwide. Thomas, please.
Thank you very much, Katie. It's a pleasure being here with you. And yeah, my name is Thomas Heege. I'm heading the German office of EOMAP here in Germany, and joined this journey on SDB since more than 20 years, both on the research side on developing these things, but as well in application, and then in partnership with many organizations, as you right now heard, to really bring this into application. So my talk, I hope my screen is shared. Yes, I see it shared. So my talk is a short technical introduction in how to further improve the use of SDB, especially here improving autonomy of SDB measurements by physics-based multi-scene processing. And why did I choose this title? Next slide. So let's look back to the value proposition of satellite-derived bathymetry. As a major reason nowadays of using this is to fill data gaps in shallow water bathymetry worldwide in many different locations under many different conditions, and data gaps not only spatially but over space and time. So also when you look to the last year's SDB day, you will find presentations and also on how to use this in industry and from coastal managers to map temporal changes. But still there are so many spatial gaps, and that's the reason of using SDB. That means the question is, what are the different ways? There are many ways to generate SDB. We all know SDB is very sensitive to errors. And just here one example, you see two different satellite images which are under impact not only on watercolor, land and bathymetry, but as well on atmosphere, haze, turbidity in water absorbers such as algae groups. And everybody who's working with bathymetry and from satellites is aware that this has an impact on quality and also generates errors. So that's the reason why we really care about the level of the levels of error corrections to maximize these corrections, because it means the objective behind that is to maximize accuracy and again autonomy. And the objective two, why we choose many years ago the physics-based way is to improve transparency and traceability. That means to really understand error sources when correcting, because when we go globally in many locations, then this transparency and traceability is very important as well when organizations like hydrographical offices take over own production. That means again, then here transparency is required and full understanding what is happening. So we developed, we started developing already 20 years ago physics-based methods to correct for this, and that's a quite long journey. Nowadays, we would say we have fully physics-based. So what is the difference between that? So we just think the level of corrections which improve accuracy can still further increase, and it's still an ongoing journey. But of course, there's some complexity behind that. That means these impacts that I addressed before, different aerosols on each point in the atmosphere, for each point that we are looking for, actually adjacency, sun glitter, water surface, and all these elements need to be corrected. And there are actually ways to, on one hand side, use forward radiative transfer models. It means highly accurate models who can describe what is happening with the light on the way from the sun through the atmosphere in the water and back, what is happening then with a signal to the sensor. What we are doing here is inverse way. That means we try to interpret the satellite radiance images due to these different impacts and correct these. So it means for each pixel we try to calculate the aerosol properties, the adjacency impact, that means the scattering impact from the land side, sun glitter surfaces, and also the in-water optical properties. So the standard physical procedure means going through these different modules, partly coupled, because you have partly to solve this in one way. For example, when we solve water depth retrieval, the water depths we solve at the same time the optical properties of the water and the seafloor reflectivity, including all the bidirectional effects which we have to consider as each satellite record and pixel looks from a different direction, and at the same time the sun also moves and has a different position. When starting using multiple images in one time, the process is on one hand side very simple, very similar, but the complexity starts when we want in a physical way still to resolve what is happening in the water, because that's actually a chance, because when we are solving the water optical properties with multi-spectral, mostly multi, sometimes also hyperspectral satellite sensors, then the ambiguity starts to be being an issue. That means this generates uncertainties. So we several years ago already patented a way which is quite straightforward, so easy understandable, because the depths from multiple images has to be the same if we correct this for the tidal impacts, but all the other parameters vary. And this is can be taken then from the algorithms as strengths to increase the accuracy. And that's actually the very simple procedure that we invented here, but finally needed a number of years to bring it to a form that then really operationally gives stable results. And I would like to show you what does this mean in application. So when we, for the example that I provided before, process in this case 16 scenes in parallel, then the accuracy, the completely independent accuracy, so without calibration data, increases significantly. And in this case, we come to a tolerance bound of over 90% within our standard tolerance values, which we provide here as 50 centimeters plus minus 50 centimeters plus 10%. That's not always the case. So if we have single scenes, we have all these different impacts, which we have everywhere. So on one scene and one location, more turbidity, another more sunwind in certain areas, other again high aerosol. All this together in this procedure increases the absolute accuracy. So it means we meet better the one-to-one line, and also increase the accuracy itself. So you see just exemplary some areas when we use 1, 2, 3 scenes, accuracy already improves. When we use single scenes, we can have very bad accuracies, but also if we have an excellent single scene, we have already quite good accuracies, but putting those together in a large majority of cases increases accuracy significantly. Question, how many satellite records do we need? And that varies actually on the environmental conditions. So there's not a general number that we can provide, but we realized from many areas which we process worldwide that there's a limit where the accuracy further improves. Even it is better to select, if available, several satellite records, typically the best 2, 3, 1, 2, 3, 4, 2, 3, 4, 5 scenes, rather than 20 scenes or 100 scenes, because partly we have a lot of satellite scenes available depending on the sensors. So this approach is applied to all the sensors that we process. So if this is WorldView, Sentinel-2, or Landsat. Question is, does this technology effort really matter, and is this worth the effort? It's a lot of technology invest, at least from our perspective in the past 20 years. And it also requires processing time. Still the question when accuracy is required, does this worth? So just to compare this physical way with IHO cookbook approach, which is an empirical one, we have to go into details, for example, to darker areas to see what is the difference then in accuracy, but there are further differences. So that means we increase the autonomy for all, especially the gaps that we want to close. That was the reason why in the beginning I highlighted what is the main value of a satellite-based SDB. So overlapping calibration is usually required with empirical methods, and there's the unknown uncertainty and gaps, which we can overcome if we continuously invest then to improve accuracies through the physical-based corrections, and here also the multi-scene processing. Still, there's good reason to use data when available. For example, the LiDAR data from satellites became available, not full cover, not covering the full Earth, and also not having the same uncertainties and accuracies as ship-based or airborne-based LiDAR measurements, but it can be used here to cross-validate, not in this case, not to calibrate. So still we are independent, but we can increase the safety here if we implement as many data as possible. So for us, it has been
3 minutes.
3 minutes. Thank you. Almost the last slide. So for us, it has been a long journey, as said already, on improving these accuracies. But there's another element that also matters. So we improve implicity and autonomy with this approach. Why this? So the way that you saw before on physics-based processing can be automized to a very high level as well. So it can be, you can look after what is exactly happening in each step in case that errors appear, and then that we have to modify, but you can also run this on a very automated way. That's what we put in our software, even then to license. So when we heard Commander Waterson talking about this, and that's exactly the reason where we start training, capacity building, making understanding organizations how this works, capacity building, but also with a very simple tool to let them do the work on their own. As well, the image selection. So we have online tools, but my colleagues will talk later with a short introduction into this, how easy this can be done later, still on the highest possible level. I thank you very much for the attention, and I'm looking forward also to discussion here on the online forum. Thank you.
Thank you very much, Mr. Heege, for your presentation, and you were perfectly on time. I will just remind the participants to please hold your questions until the end and then put them into the chat, and then we will go through them and have the panelists respond. So I would like to now introduce our next presenter, Mr. Philip Warner, who has a master's degree in coastal engineering from Queen's University, Canada, and over 25 years of professional experience in consulting throughout the Caribbean and North America. He has design, inspection, and appraisal experience for coastal protection, marine structures, and oceanographic studies, among many others. His experience includes work in the Caribbean region and internationally, and his presentation is going to be on satellite-derived information for coastal engineering and planning, use cases from the Caribbean. Please, Mr. Warner.
Good morning, good afternoon to everyone. Thanks for that introduction. I'm just trying to figure out my PowerPoint screen sharing capabilities here, and I hope that everything will work out. I'm not too sure which. Apologize for the delays.
Philip, we can see your screen. It's the agenda which you have on the screen.
Oh no.
Now it is. We see your presentation in the first slide.
Ah, excellent. That's very good. All right. Thanks for the introduction and thanks for the pointers as to what screen I'm sharing. My name is Philip Warner. I'm a coastal engineer. Been working in the Caribbean for geez, actually more like 30 years when I really count them, but I'm going to make a presentation today really based on the use cases for satellite-derived bathymetry. And then first I just want to explain who we are and what we do, and then I'm going to go through a number of examples showing how we use the data for our engineering designs, for our coastal risk assessments, and as part of our monitoring programs. So who are we? Well, Smith Warner International is the largest coastal engineering firm in the Caribbean. We specialize in marine-related environmental impact assessments, oceanography, construction and supervision of coastal engineering projects. We founded the company in 1995, and we've grown from just a couple of people to a complement of around 30 people working in the field. We have a lot of engineers, mostly engineers and environmental scientists working for us, a lot of postgraduate trained coastal engineers. And we have 3 offices in, actually 4 offices in the Caribbean. Our head office is in Kingston, Jamaica, and we have branches in Turks and Caicos, Trinidad, St. Lucia, and I actually work out of my home office in Canada. What we do, we sort of break it down into 5 different categories. We do planning, including shoreline and coastal planning, climate change preparation, and disaster mitigation. We do design, particularly of resorts and recreational beaches, shoreline stabilization, ports and marinas. We do assessment, environmental impact assessment, natural disaster risks and hazard assessments, including storm surge and hurricane. Implementation, we do contract administration and project management of construction projects, as well as a full design build of our designs. And lastly, we do quite a lot of monitoring, oceanographic monitoring, measuring currents, nearshore currents, of course, bathymetry, shoreline movement, as well as coastal structure damage assessments, or monitoring rather, sorry. So why do we, as coastal engineers, use SDB? Well, our market is the Caribbean, and there's a lot of ocean in between there, and to get from one island to the next takes quite a lot of time. So SDB allows us to reduce our travel time. Field work carries certain risks. This image shows what can happen when you show up one day to do a bathymetric survey and the weather isn't cooperating. Hold on. Traditional echo soundings have only lines, and we need to fill in those gaps because good numerical models and engineering requires the best possible input. So as I said, I'm briefly just going to go through some of the projects using satellite-derived bathymetry, and you can get an idea of why we use it and how we use satellite-derived bathymetry. Our first project is on the eastern shore of St. Vincent here, which is quite exposed to the Atlantic sea and swell waves. And the site is actually a new sandy bay village up here on the east coast, and that's where that video showing the rough waves was taken. So this is the site. The problem there is there's been considerable shoreline erosion over the years. It's quite a remote location. And the coastal erosion has washed away several buildings and is putting the main road in jeopardy, as well as the infrastructure that runs along that road, the power lines and water supply. So it's important to provide protection to that critical infrastructure. The challenge at that site was we really needed to create an accurate digital elevation model for the entire study area, as we needed to combine a coastal protection design with a drainage design. And the site was very difficult to access, as I demonstrated before with the video showing the waves. There were no boats locally available for, or not no, but boats were difficult to obtain locally due to the rough sea conditions. There's no marine infrastructure there for launching boats. They've had to come in from adjacent locations around the island. And as I said before, the site is quite remote, so access was difficult. And so our solution was really to obtain satellite-derived bathymetry for the areas between the reef and the shoreline, and augment that with RTK GPS surveys for the topography and along the nearshore area. And we also had access to an island scale LiDAR, but unfortunately the LiDAR was not tied to a good datum, so we needed to be correcting the LiDAR to the RTK surveys and then merging that with the nautical chart area and the SDB to create an overall DEM of the site. And this is what we put together, and that allowed for us to run the hydrology and hydraulic models for the site, as well as design the coastal protection structures and integrate the riverbank protection and the shoreline protection designs into a holistic solution. And the SDB allowed us to have accurate modeling to define the design conditions for the shoreline protection, as well as combining that with the nearshore profiles. We were able to get accurate quantity estimates for our engineering design. And here's just an example of our engineering design showing the extents of the works, as well as a cross-section of the design we came up using this X block armored protection. The next example I wanted to present to you is in the island of St. Kitts and Nevis, here in the northeast corner of the Caribbean. The site is located here on this tiny bridge of land going between, or just south of on the southern portion of the island of St. Kitts. So the challenges at this site was, again, we needed to create a digital elevation model for a public beach enhancement project. And we had a boat-based single echo track, echo sounder track line, but it was not sufficient. There was significant gaps between the lines. We're missing the reef and seagrass areas. Oh my goodness. We also, the challenge there was we wanted to have very accurate sediment transport calculations. So we needed to have a precise numerical modeling because the wave conditions of the site were quite bimodal due to the local sea waves coming from one direction and long period swell waves coming from an opposite direction. So generating sediment transport in both directions on the beach, depending on the prevailing wave conditions. So we needed accurate modeling to be able to understand those processes.
3 minutes.
Oh my goodness. Okay, I will zip ahead. Sorry for the delay. This was the site in the SDB that we got. Here's just an example of how we integrated the beach profile data here with the track lines and the satellite-derived bathymetry. And I'm zooming in to show our numerical model, grid resolution and the light gray lines there, and the need to have multiple data points within our numerical model is shown here on the last slide. This is the solution that we came up with. So just a quick demonstration of where it's going. I want to quickly zip to the final example, which was in a hotel development in St. Lucia on the west coast. And I just want to go through sort of more of the process here, where we would take our satellite-derived bathymetry and echo sounder track lines and beach profile lines, and we combine that with wave information from global wave models and establish design conditions at the site. And what I wanted to get to here was just basically the quick overlay of how we combine all these data sets together. So the first one here shows our bathymetry, and then we overlay that with the seafloor classification, which is also from satellite-derived seafloor classification, as well as ground truth with traditional transects. We then use our numerical models to calculate the wave conditions. We then add over those waves generate alongshore and cross-shore current patterns, which our models are able to predict. And those combined waves and currents generate sediment transport. And you can see here that the main sediment transport in the yellow is concentrated in the areas which were defined by the seafloor classification as sandy bottoms, which is expected. And this allows us to predict shoreline morphology. So we can see here that the sediment is moving from the upper beach to the lower beach during this particular swell event. And this combined data allows us to come up with some concepts to solve the beach erosion at this particular site, and then subsequently we'll be able to look at impact assessments, final design, and ultimately construction. So briefly, we've been using satellite-derived bathymetry since 2017. We've basically got it fully integrated into our workflow, and it allows us to fill in the data gaps between our echo, sound, and track lines. This leads to improved confidence in our numerical modeling and allows us to collect bathymetry in challenging areas due to access, safety, and travel considerations. And we augment that with our SDB with echo soundings and beach profiles where practical. We also have looked at coastal change, more like a shoreline change and reef degradation. So this is sort of looking at time snaps, comparing bathymetry or seafloor classification over time. There's a potential to look at as-built conditions, but that we haven't undertaken that. And to us, as I mentioned before, the seafloor classification is helpful to us. It allows us to integrate that information into our numerical models. And we've also undertaken shoreline change monitoring using satellite-derived information. Thank you very much. That's the end of my presentation.
Thank you very much, Mr. Warner. And I do see that you have at least one question in the chat. We will now move on to our next presenter, who is Stefan Rump. He is a geomatics engineer with 14 years of professional experience in hydrographic processing. He is leading the hydrographic processing and cable route charting department at Vrignaud, Germany Marine, and is responsible for the preparation and quality control of corresponding data and charts, including SDB products. So the title of his presentation is Close the Gap, SDB for Pre-Installation Cable Route Surveys.
Yeah, thank you very much. Can you see already my screen? I hope so.
Yes, we can see your screen and all good.
Perfect. All right. Yeah, my name is Stefan Rump. I'm from Vrignaud, Germany Marine, and yeah, my presentation today I will talk about SDB for pre-installation cable route surveys. So starting with our work for the subsea cable market, giving some examples for seamless data from deep water to topo, and that includes also the SDB products, and close out with challenges and benefits. Okay, starting with this map, that's published in 2019 by the New York Times, but it's still valid information shown. People think that data is in the cloud, but it's not. It's in the ocean, and all cables visible here are subsea telecom cables in service by 2021. So already now for all our online work or this virtual SDB day, we rely on these backbones of the internet. And yeah, we are taking care that these cables can be laid safely. And as a statement, what Vrignaud's work is about, the installation of offshore cables requires a detailed knowledge of the seabed conditions. And investigation of the seabed along the proposed route is regarded as an essential requirement for the planning and execution of cable installation. So this is currently our fleet. We are executing this surveys with the Vrignaud Discovery, Vrignaud Gauss, and Vrignaud Supporter with their launches. And all of these vessels are equipped with state-of-the-art multi-beam echo sounders, side scan, sub-bottom magnetometer, and all that can be supplied simultaneously. And they are also equipped for sediment samples. Giving an overview of how such a cable route segment can look like. Starting in the west, here at the branching unit in the deep water section, followed by the shallow water section, also shown with coverage of the multi-beam. Then the inshore survey is normally conducted by the launch. The tricky part is here, the surf zone. We will come or talk about later, that one with SDB, and also the topo survey. So this one is the detailed landing site. The inshore survey is covered by multi-beam data. Also, the topo site around the beach manhole is covered with topographic data. This is also possible to be done by the survey crew. So the vessel is equipped with all needed equipment here. And the only part that is not possible, or mostly not possible to close, is in the middle. And that will be left for SDB. So even if we make benefit of tides and doing the inshore survey at high tides and the topo survey at low tides, the gap mostly remains. In former times, we used the diver swim survey along the route to get some information, but due to HSE risks, that should be avoided. So SDB is a very good application for us to get suitable data to fill this gap in the surf zone. But that's not the only one. SDB from our business can be applied for planning, mapping, and monitoring. So starting here with a desktop study, inshore bathymetry for planning could be derived from SDB. Also inshore survey, an extent full coverage from only a single multi-beam survey line could be achieved. The example what I just showed is the landing fill gaps between inshore vessel and topo. And in the end, monitoring create time series of SDB to predict future seabed changes. So planning, mapping, monitoring, all is important. So have a look at the example here for creating a seamless data set. The inshore vessel stopped at 3 meter LAT water depth, and the gap to the topo is about 200 meter here. And this is the result after SDB is fed in. So the 2 meter and 1 meter contour could be added, and the data sets overlap on both sides. And on the lower left part here, the seabed profile is visible, and yeah, it's close. So we have a general morphology information gathered from SDB, and we have full coverage here. This is another example, 140 meter gap. It's quite similar approach. Here the SDB is almost closing the gap, but it's not entirely surveyed. And that's what we saw at different places, that SDB is giving the general appearance of the morphology, but what is sometimes not possible to get all the corridor covered with data. So also the difference is obviously visible. The multi-beam data in the south has a higher accuracy. So we have 0.5 meter or even more, and it's a high accurate survey. The SDB data is calculated from, or the input is Sentinel-2 images with a 10 meter resolution. So it's clearly visible that a feature search in the SDB area is not really able to detect 1 or 2 meter object that can lie on the proposed cable route, which is displayed here with the red line. So we thought about how to classify these surveys. As we are also working in the hydrographic survey business and doing surveys there, it's clear to us that our multi-beam survey data could be classified as IHO special order or CATSOC A1. We thought about how to classify the SDB data, and not to overrate the data set. We said it's CATSOC maybe C, because of the missing feature search. Okay, coming here to some challenging environment. So problematic areas, as already stated, it could be whitewater. And in that case here, with this image taken, it's not possible to get any information of the seafloor. But going through the archives, it is sometimes possible to find a suitable image with less weather impact or less clouds or less sea state in that case, so that it's only a matter of finding the right image. The same applies here to this example. This is the red route is going through this very shallow basin, and all the dust, or it's like foggy appearance, and it's not clouds, but this is turbidity in the water column. So this is also hindering a reliable depth result in that area. So, but sometimes it changed with, if you pick different images over the year that disappear, and then maybe it's possible to get a result as well. So there are challenges, in that case environmental, and also the classification with regards to IHO standards is for me not 100% clear, but in the end we have a lot of benefits from our side. So SDB is low cost in comparison to applying a diver. Its global coverage is available. It's also accessible to remote locations. It's easy to process, and it's also reducing HSE risks. So overall, we are very happy that we could use the SDB analytics and also close the gap on many landing sites and have a seamless data set in the end. All right. So thank you for your attention.
Thank you very much. Our next presenter is a colleague of mine from my agency, the U.S. National Oceanic and Atmospheric Administration. Dr. Richard Stumpf is an oceanographer who works with our National Centers for Coastal Ocean Science. Dr. Stumpf has over 30 years of experience in coastal oceanography. He develops methods to make satellite data and modeling useful in understanding and managing coastal eutrophication, habitat change, shallow bathymetry, and algal bloom forecasting. He has his BA degree in environmental sciences and MS and PhD degrees in marine studies from the University of Delaware. Dr. Stumpf.
Okay, thank you so much, Katie. Can you see my screen? Okay, excellent. All right, thank you, Katie and Edward, for allowing me in this session, and Thomas for putting together this this conference. This is a great opportunity for us to at least meet, and hopefully the next one we will all be in person. That would be wonderful. Okay, you've SDB, as you've gotten from the other speakers, and many of you know, was developed as just a result of observing the seafloor in clear water, which of course occurred mostly in coral reef areas. But as it's developed, there's increasing interest in other areas where waters are not always clear, which leads to turbidity questions. And how do we approach that when we do have transient turbidity? There's also concerns about how do you select scenes and so forth. So what I'm going to touch on is research we're doing in order to pull this together to push forward our ability to map within NOAA and also within Spain. My colleague Isabel Caballero, who's with the Marine Science Institute of Andalusia in Spain, and great to talk. So let me go through here. Okay, typical areas of interest have been coral reefs, like in the Pacific, the Florida Keys, and these are often clear water areas, although Florida Keys actually do have transient turbidity. Hurricanes come through, but cold fronts in the winter. And then, of course, we get into issues, very critical ones, of inlets and capes and shoals, which experience, again, transient turbid water of different sorts. This is actually an example of a satellite SDB superimposed on a nautical chart and one inlet, and other examples. Common SDB methodology, the one we're applying, going back to algorithm in 2003. It is in the IHO GEBCO cookbook. There's a step-by-step instruction using ArcGIS. And typically in that application, it's relative depths are deployed. They don't necessarily convert to absolute depth in those cases, although that's, people are obviously, that's the main concern, is getting to absolute depths. Now, as far as the methodology, I'll note on this that we get some confusion on empirical and physics and that sort of thing. There are truly empirical algorithms that are, say, machine learning, which require huge amounts of field data in order to calibrate those, and they would be very specific. You're on the other side, as Thomas noted, where solving the radiative transfer equations as a full physics solution. The method we have is an approximation of physics of light and water, and light is attenuated exponentially into water, so it decreases very rapidly at first and slows down. And what that means is a depth itself is the logarithm of what you receive back, the amount of light, is proportional to the depth. And so, as example of that, if you take the logarithms, this is green light and blue light, we end up with linear patterns, and at different depths, they will follow straight lines. So from that, if we're using two wavelengths that have different absorption, we can use a ratio of those logarithms, and we can come up with a depth. So there's again, this is an approximation of physics. This is not the radiative transfer equation, but it describes the physics. The coefficients do require empirical tuning, but we don't need much data. We typically use about half a dozen, about 6 to 10 points for this, and in fact often use those off of available data, off of charts. And the model's been used successfully in many areas around the globe by many people. A key part of this that I'll touch on later is the ratio itself, which we call the pseudo depth. So it's a linear relationship to depth, and that comes directly out of the reflectances that are atmospherically corrected. So when you see that, when I use this term again, PSDB is pseudo depth or estimated depth. Okay, result example in clear water. This is from Puerto Rico, Buck Island. Here's a LiDAR map and then the SDB, and you can see all the patterns show up. And this is, of course, clear water, so we're going down to 20 meters in this case, and clear information all throughout. A huge value, as we all know with SDB, is we get far more extensive information than you can get necessarily from a LiDAR survey. So that's just an example. And we also analyzed the atmosphere correction we applied, which was Acolyte, and it gave consistent results across multiple scenes for this whole study. And that's in a paper you see here we published in 2020. Now about turbidity, here's some scenes. This is from Cape Lookout on the North Carolina on the US East Coast. And you can see there's turbidity patterns in the water, a lot more on the October 30th. It's kind of a slightly browner tinge. And when we talk about false shoals, let's just work through this. So this is a measure of the amount of turbidity in the water. And if it's dark blue, it's very low turbidity. If it's light blue, it's moderate. And the reds, yellows and reds are very high turbidity. So you can see the differences between the scene. But even the January 23rd is not completely clear. We estimate the depth, and these are depths in meters. You can see the turbidity pretty much obliterates the depths, saying that we have about 2 meters of water going well offshore throughout the area. But even this moderate turbidity, we end out with underestimates of the depth overall. So this false shoaling issue. And between these, where we have LiDAR, we could still retrieve pretty well on the January 23rd. Median errors against the LiDAR survey of about 1.6 meters, which is not optimal. But you can see how severe that is on the October one when we're at a much more severe over 3 meters error, which is really unacceptable. And in fact, error is going well out to 10 meters. Basically, in 10 meters of water, it's saying there's it's 1 meter, which is a real problem that would have to be addressed. So it's clearly transient. So the current approach is pick the best scene, and you'll have a little task here of going. If you look through these, which would be the optimal scene to use? In a few slides, I'll show you the answer when we do a comparison to our final method. So that's the approach. You go through all the data and you look for the scene that looks the best. Well, how can we reduce turbidity and labor? Well, our first take on this is if we don't select the scenes, but we use all of them, then we have an opportunity here. And the idea is to composite that together. Well, what's the basis behind doing that? If we look at the values before calibration, the pseudo SDB, we can see that there's a very clear relationship between that and turbidity. If this is high, it's deeper water. If it's low, it's shallower. And as the turbidity increases, there's a very clear, clean, linear relationship where the relative depth decreases against turbidity. So at the lowest turbidity value, we will get the deepest water, which is what we want, the most accurate, and this is the most accurate, the least biased water samples. So, and these are all, by the way, this is the same pixel from multiple scenes having different turbidities. So we know from LiDAR the depth is 12 meters, the LiDAR is 8 meters, and in fact, you can see in the relative, these drop off in the SDB. That's the point we want. So our goal is to composite what would be the clearest of all the scenes, the clearest pixel from all of each scene. So going back to that, instead of picking one scene, just collect all of them and go through this process. Again, this is published in our paper in 2020. The atmospheric, this is in remote sensing, atmospheric correction in 2020. So we calculate the atmospheric correction for all of them, for all the bands, red, green, blue, red edge. This is Sentinel-2 data, by the way, that we're using. You could do similar with Worldview. We then convert them all to pseudo SDB. And this is, again, there's no manual intervention involved here. It just runs as part of the process. We then take at each pixel, and here's a hypothetical pixel. We check for each one for which is has the lowest turbidity from the whole set of scenes. We then generate a composite. So this was the lowest turbidity, deepest depth of all of these. So that's the one that's dropped in that side. So this composite is then generated. And at the same time, we do turbidity composites of the same pixels overall. Again, there's no manual intervention involved with any of this process. Next step does require some manual determination, and that is to calibrate to water depth. So we take the reference depths and combine them with the turbidity. And this is an example of an actual calibration. 9 points were used for this calibration off a nautical chart. I should say we didn't use a LiDAR survey to do this. So at that point, then we apply it, and we end out with the SDB water depth as a result. So one manual intervention, the rest is all automated overall. If we compare that to clear a scene, and if you had asked before which one it was, November 27th was the best case, you can still see, if you look, there's a little residual turbidity here, and also on the shore, along the shoreline. But let's compare that. Now, so the first point is, of all the scenes we ran through, and there were more than those 8 you saw, on the comparison, only 4% of the pixels came out of what we would call the clearest scene. There were 4 other scenes that actually provided most of the pixels that we could use for the nearshore comparison with LiDAR. Only 4% came from this scene. So already we have a challenge that our assumption about what is an optimal scene may not be the best in practice. When we look at this scene, and we look at a turbidity metric, we can see very bright red right along the coast, and also in the lagoon behind it, again, Cape Lookout, which when we do the composite, all of that disappears. We still do have some slight residual turbidity in here, but it's dropped off enormously for the overall numbers. When we go to SDB calibrated, we can see striking differences here, particularly on the nearshore areas overall. That's actually an ebb tidal shoal. There may be a hint of a bloom here that's still not resolved. However, we do have the turbidity information to address that. When we look at the overall accuracy, the best seen, median error of 0.8, the intercortical range of 1.6, we can see how dramatically we reduced that. We're under half a meter, 0.4 meters for the median error overall in a very tight relationship. So we have a very strong pattern. Was that a 3-minute warning?
2 minute.
Okay, I'm just about done. We'll note also the calibration can work in more than one area. That Cape Lookout calibration we applied to a site in Florida, which is well away from North Carolina. And we ended out with the same error metric. This is the 1-to-1 line for that region, all in the 1-to line. And again, 0.4 meters, applying one calibration to another area. So these calibrations do not necessarily have to be redone for each case. Again, this is with a composite. And a last bit here, question about change detection. We just have in revision a paper on doing change, comparing the LiDAR to SDB, and these are actually accretion and erosion depths. And the change difference was 0.4 meters, which was about as good as the actual error on the individual depth scenes. So we're actually pulling out pretty much the same pattern. And you can see various features. These are color-coded, how well they align. These are all accretion features, up to 3 meters of accretion that were all picked up in using this method for composite before and after hurricane. So we're at the point of potentially doing change analysis in order to address this with far more information than a LiDAR survey as well. And in general, a summary of the method, we're using this on our SDB method. The reduction in labor, we do not have to pick the best scene, do not have to select it. Every scene does not need to be calibrated, only the final composite. Only a few calibration points are needed. And very importantly, in none of our work have we used new surveys for this. We've always used chart data in order to validate this. So errors that we report, we might very well be able to get better if we even used finer charts. We can identify areas influenced by residual turbidity, and that impact can be estimated. We've come up with estimates of how much the depth will be impacted by turbidity, suitable for change analysis, and also we have a method to get better results in very shallow water. We've been applying this around the US and from Puerto Rico up to New England as test cases, and we're now starting this in Spanish waters in the Mediterranean as well. And so we're looking at this. Our goal is to implement this as a routine capability within NOAA and potentially expand this also within Spain. And thank you very much.
Thank you very much, Rick. Our last presenter for this session is Dr. Knut Hartmann. He has already introduced himself as the operating officer at EOMAP, and I'll just expand on that a little bit. He is an Earth observation geodata expert. He has degrees in geoecology and a PhD in natural science. And prior to joining EOMAP in 2011, he worked in the geoinformation section of an engineering company, as well as the German Federal Research Center. So throughout his career, he's developed and applied solutions for different applications and across a range of industries. Since joining EOMAP, he's been involved in various projects ranging from the higher latitudes of Greenland down to the Southern Pacific. Oh, yeah, please.
Thank you very much, Katie. Thanks for the introduction. So I run the screen share. And please just give me a signal that you can see it actually.
We see it.
Perfect. Thank you.
See it.
So yeah, thanks again, Katie, to the introduction. I'm actually wearing two hats here. So yes, I'm representative of EOMAP, but more than that, today I actually want to put your attention to a project which is called 4S. So I'm also in the position then of being the project leader for this project, and the purpose really of this pretty short presentation is actually just to raise the attention on this project and actually the things to come within this project. So really the entire project, which I briefly introduced, it's a team effort. Yeah. So we are not only one company, we are a team of 8 entities and a lot of people, a lot of experts here. And just to give you the name of the partners here, starting from left to right, we have Smith Warner, so Philip, actually, which you have been introduced earlier, is part of the team with his colleagues. We have the hydrographic office of Portugal in the team of researchers, as well as the software developer QPS. We have the governmental agency of Sweden, Länsstyrelsen and Västerbotten for northern Sweden, Fugro, and EOMAP here is project lead, and research institutes from Italy and Greece, ISMAR, CNR, and HCMR. So this is us. Obviously, there are more than just those entities. It's a person and experts which are working on that. And all these experts actually have in common that they have background in hydrography, in benthic mapping, in IT, and obviously satellite image analysis. So all this stuff which you actually need in order to develop a smart solution for using satellite data. So which brings us actually together, and our ambition really is to generate in this project an automatic and accurate Earth observation mapping and monitoring procedure for shallow waters. We spoke a lot about depths, obviously, yeah? But there's more than depths. So there is a lot of information which is in the shallow waters, which is of high importance. So the information on habitats, on the benthic habitats is crucial for a lot of things, including reporting, environmental agents, impact assessments and stuff like that. And it's dynamic. Seagrass meadows change and stuff like this. So within the project, we want to have a focus on that, depth as well, yes, but also we want to characterize the seafloor. And we do not only want to limit us to satellite data, we want to apply technologies to new sensors, to drones, for example, or also use active LiDAR systems, such as the ISAT data set. There's also some recent advances in hyperspectral data, which we haven't looked at. And we actually want to develop this as a software tool. And I hope these things work now. Yeah, here it comes. So we want to actually work and provide software tools so that actually stakeholders, users, such as you might be one, are able to use this, which means we want to make those tools pretty easy. So QPS, for example, I mentioned, they are already have a very, very professional software suites for hydrographic data cleaning and stuff like that. So we are working together with them to make SDB data as part of the solution. To the image in the middle, you see how we combine drone with satellite-derived bathymetry data in order to increase the level of detail. And in this example, it's a level of detail of 9 centimeter spatial resolution, which we have reached. And I mentioned we want to make this easy and comfortable for the users to apply. And therefore, we develop web applications. So that's our ambition here. The solution sounds very simple. We want to develop online tools which empower stakeholders, users to map and monitor seafloor habitats, morphology, and depth from the comfort of their desk. That's very simple. That's our solution which we are after. More technically, you can see that it actually requires a lot of work. So it requires a cloud-based Earth observation workflow, not only one, workflows, which have interfaces, user interfaces, but also machine interfaces to access these highly optimized algorithms to perform spectral and AI analysis on satellite, but also other image data. And what you would receive is a return of geospatial data on bathymetry, benthic, or other derived data sets. Or perhaps not even data, perhaps only information if you like. So, and why do we do all this? Is we actually want to create a value. So we want to reduce efforts which you have to spend for campaign planning. We want to actually achieve a better information and decision-making data set, which means we by using this data, you can do analysis back in the past and understand on how, for example, the seabed meadows have been like 10 or 20 years ago. So we want to give you these kind of data sets which are actually very often crucial to base your decision on. And yes, of course, the beauty here of this remote survey methods is they come with reduced costs. So these are the benefits which we are after. And obviously, this stuff is working in progress. So the project actually has started in end of last year, so in November 2020, and it has a duration of 3 years. In this very early project phase, actually, we are looking for your input. So we really want to ask you to take the chance to define your requirements on a system such as this. So it is really your chance to interact with us, to give your feedback where you see there is a need, or where you see where is, let's say, your highest pain. And for that purpose, we have an online poll at the moment, online questionnaire actually. So this is a link which I will share in the chat formular, but you can also find it in the sdbday.org webpage. Simply go to the contact form as it's shown here in the video, and to the bottom of the page, you will find that the link to the questionnaire. So I would ask you to do that, and it takes about, I think, in average like 5 minutes of your time, and you can really help us to be more tailored. So this is the way for you to interact with the project in the very first stage. Later on, actually, when we work on R&D and do our test cases in practice, we are always interested to receive feedback, and of course are always interested to receive data to compare with and stuff like that. So have an eye on the project. If you feel like this will be important for you, send out an email to the project email address, which you see on the screen. We'll keep you updated on that and contact you, and really consider this as a chance to form a tailored solution which is actually fit for purpose. I mentioned the strong thing here is it's not only for bathymetry, we have an eye on the benthic, especially because there's a high demand also on accessing these kind of information. I promised it would be a short one, so I hope it was. Thank you very much. And I hand over to Katie again.
Thank you, Knut. So we are now at the end of all of our presentations, and I'd like to thank all the presenters for some very thought-provoking and very interesting presentations. And I have already captured, there were several questions that came up in the chat during the presentations. So I'm going to start with those, but I will also ask anyone else, any other participant who has questions for the panel, any of the panel members, to go ahead and put those into the chat. So the first one was for Thomas. I think it may have been responded to in the chat, but I will just ask to be sure. The question was, can you filter out bottom reflectance, scattering, absorption signals to infer seafloor composition, sand, clay, silt, etc., or properties, firm, soft? So Thomas, would you like to respond to that?
Yeah, thank you, Katie. So, and for the question, so it's a clear yes.
One stop, Thomas. Can you turn on your camera, please, when you reply?
It's not possible. I'm not allowed. Maybe you have to give me the allowance. Video starting. Yes. Okay. So yes, thank you. It's a good question, really, to understand what we are doing here, and it's a clear yes. So the process itself calculates the absorption scattering properties in the water for each pixel, and the underwater, the seabed floor reflectivity as well. And that's actually in many projects further used than for seabed habitat mapping and so on. But I think answer is yes.
So Thomas, you can remain on the screen because the next two, I believe, are for you as well. The next one is, thank you for this great opportunity to learn more and exchange knowledge on the fascinating field of SDB. What are the advances in accuracy that you have observed using the ISAT-2 data for calibration in comparison to your unsupervised analytical satellite-derived bathymetries? Or did you use the ISAT-2 data only to validate your automated estimations? If the latter, what is the approximate level of error based on the maximum estimated SDB?
Yeah, I will start with the first part of the question. So thank you. While I saw this, I brought this question back to my team. And more, as mentioned in my talk, so this is actually mostly used, and that's also our recommendation to cross-check than the outcomes, because still you may have conditions where yeah, you can improve this, but mainly it is used to cross-check. But you need to know that the ISAT-based bathymetry is also effort to process these. So we have an online tool as well to process these in full waveform to generate bathymetry. Still, there is a manual cleaning required that these data are good enough then for validation. And in some cases, yes, when you see larger gains consistently between these data, that they can be used also, but that's not the usual procedure for us. For the accuracies, I may need to hear this question again. Maybe even Knut listens with me, and that we can answer this better. So what was the question on the accuracies? I'm sorry, I was not aware.
Let's see, asked if you used the ISAT-2 data only to validate your automated estimations. If the latter, what is the approximate level of error based on the maximum estimated SDB?
Yeah, from the physics-based processing, or from the ISAT. So that's why I, at the moment, not sure what is the question about.
Let me step in. I think I got it. So the point is, the question obviously asks the question if these LiDAR data sets, which are actually hot topic at the moment, are being used for this validation. Thomas replied correctly. What needs to be, should not be forgotten, these ISAT data come with uncertainties themselves. Yeah. So typically you want to validate with data set which you can fully trust. So, and to date, this is actually airborne LiDAR or multi-beam data set or even single beam acoustic. So in this ISAT LiDAR data set is okay, but it's on its own, it's not super accurate. So which means we will not validate, it's more like a comparison of this kind of data set. If we don't have these data or any other data and run our models and validate it against other acoustic or LiDAR data set, the answer is that these uncertainties of the depths depend a bit on the local environmental condition, as pointed out by Thomas earlier, but in general we speak of a depth vertical uncertainty of 0.5 meter and 10% depth dependence. As said, there are always ways when this environmental conditions where this accuracy cannot be met. That's what we of course try to avoid and try to point out when we do the processing. But that's as a let's say as a general understanding, you can use this value. What you also need to have in mind that there are also different ways of how you can specify good or bad. So for example, in Richard's presentation, we found the validation of the RMSE as information on the uncertainty. Root mean square error, which is a fair thing for hydrographic purposes. Actually, you typically use something like the confidence interval of 95% of the data, which is completely different and will completely result in different kinds of uncertainty. So you also need to understand actually what you're looking after. for this kind of vertical uncertainty understanding. Long answer, sorry, but I had a small presentation.
Okay, there's one last question for Thomas. Congratulations for this stunning work. The method, I believe it's ZI equals Z, considers that depths should always be the same. However, after a major event such as storms, do you observe changes in the bathymetry?
Yes, that's true, very true, and that's why the team usually limits the time frame of images that are used here. And but it's locally, there's strong local dependencies, so there are areas which have a faster change in time, and there are others which are stay stable. So, but surely yes, that's also why I mentioned that we typically try not to extend the number of scenes used, also for processing times. Thank you. Yeah.
Thank you, Thomas. The next question is for Philip Warner. Could you please expand on the problems you had with the LiDAR data for St. Vincent and how SDB data overcame or assisted with that problem?
Okay. Well, the LiDAR data was actually only topographic LiDAR, so we didn't have any overlap between that data and the satellite-derived bathymetry. So we had to use the RTK GPS survey information in order to correct the topographic LiDAR data. And the problem with the topographic LiDAR data was that it had been collected without proper reference to a datum, and the datum was sort of assumed. So we did find some corrections had to be made to that LiDAR data set in order to bring it in line with the RTK data points. Hope that answers your question.
All right, thank you. We will go on to the next one, which was addressed to Stefan Rump. The question is it possible to use SDB data with resolution better than 10 meters to fill the gaps?
Yeah, I'm not allowed to start my video currently, but I think you can hear me anyway. So thank you. Yeah, I think it's definitely possible to use also 1 or 2 meter satellite images. Currently, we have a license or in use from EOMAP Geolutics, and there the Sentinel-2 images with 10 meter resolution are given. So this is our basis, and yeah, for a quick turnaround, I think that's very important for us as well to have the opportunity to create or to process the SDB ourselves and not going back to EOMAP for each question for a landing site. So I think that's also need to be considered in that case. But in general, I can say it's possible, yes, for flows.
Thank you, Stefan. Unfortunately, we are out of time, and this is always the challenge, is to balance the discussions with the time available. There were a few remaining questions to all of the panelists. I would invite them to please look in the chat for those, and there were a couple for Dr. Stumpf as well. But I am going to have to close this session right now. And we'll turn it over now to Edward Albada, who is going to chair the next session.
Thank you, Katie, for that, moderating that, a very interesting session. We now turn on to session 2, which is more a hands-on workshop of the software that has been developed over the last decade or more. I have a quick introductory presentation to give, and then I will turn it over to my colleague Christian Boedinger, who will actually give a hands-on demonstration of the software. So without further ado, let me start this quick presentation. Oh, okay. So yes, this is the introduction to SDB tools and some of the standard challenges that are faced by SDB practitioners. You know, some of the challenges that I experience. Number one is how to identify satellite data or satellite imagery which are suitable for satellite-derived bathymetry analysis. How to create SDB data without having training data, reliable soundings or survey data. How can I QA/QC the data? How can I validate and verify and then QA/QC the data? And how can I do all of this without spending too much time and money? So we've understood these challenges and combined it with some of the underlying requirements which we've seen talking to people and practitioners. And some of the underlying requirements for our software were based on these three principles. One, it has to be easy to use. It has to be a great user experience and be able to be used by those who are relatively inexperienced with SDB technology. There should be no dependencies on costly third-party either software or hardware. And it should be reliable, repeatable, standardized, and fully transparent. So with that in mind, we've developed our software tool, which we license out for users. And I'll just introduce a couple of those. One is the EOLytics Swift. And the problem here with the first problem that I mentioned is trying to sort through these thousands and thousands of satellite imagery to ascertain which ones would be the best one for use. SDB always starts with satellite data, satellite imagery, and data from satellite imagery. And there's an immense collection of both archived as well as ongoing images collected. In fact, there are several hundred million square kilometers are recorded every day, and those are automatically archived. So, but not every satellite image is usable for satellite-derived bathymetry. There are issues such as sun glint and haze, turbidity. I think some of the other presenters mentioned this before. So selecting the right data set out of those archives is typically quite a time-consuming task. And for this reason, we've developed EOLytics Swift. It's an online tool, and it can be used to access and classify archive satellite data for feasibility in SDB imagery. So a short video of how it's used and the demonstration of it. It's an online web app. You only need your browser. And you go ahead and you select your area of interest. You can select multiple locations. And once you do that, you go and click Find Image. And then the process will start working. And then it includes a ranking of multiple images based on clouds, turbidity, haze, and so on. And then you see all of the results. And there's a quality score from 0 to 100. Of course, 100 is perfect, 0 is not usable. And you can then download the data, or then you can further on filter the data by date. So you only want a certain time period. You can filter that data and then click Apply again. And then it will filter the data for you, and then you can download the data from there. So it saves hours and hours of looking through various databases and trying to find a suitable image for use. Next slide. So how can I create, once I have the image, how can I actually create the SDB, the satellite, the actual data itself, the satellite-derived bathymetry? And for this reason, we've developed another tool called Watcor-X, which actually uses our physics-based modeling, the solution of the radiative transfer equation. So we model the light path from the interaction from the sun to the seafloor and then back to the satellite sensor. So through modeling this light path, it's possible to calculate depth, as Thomas had mentioned in his talk. My colleague Christian is going to demonstrate the use of this Watcor-X, and this will be in the next slide. So I'm just giving this as a very brief introduction that we do have a tool that can be used to actually, after you select the image or images, you can then go and actually select the or process the SDB data. Once you have data, after using Watcor-X or whatever processes you use, how can you verify and QA/QC the data? And post-processing can be done with tools, which a lot of people might be familiar with. The standard GIS or hydrographic software that can be done. SDB are either point clouds or georeferenced raster files, and you load it into anti-GIS or hydrographic software, and then you apply the tools within those packages. And QPS has a notable software for that. Vertical uncertainties, they come as modeled uncertainties based on the sensitivity analysis of the model. If you have a few survey lights, it can easily be checked. There are some SDB typical challenges that have to be manually looked at, such as selecting the best cutoff depth, for example, where the water gets too deep. And there are tools within Watcor-X that can assist with that. And then, well, this has been identified in a number of the previous presentations, but there is an active LiDAR sensor, a satellite LiDAR sensor called Watcor-X. This sensor provides some sparse track lines. It's not a total coverage that you would get from satellite-derived bathymetry, but those track lines can be used for calibration. And EOMAP can provide that data as a separate data set for these calibration requirements. This will be my last slide. It talks to how can I do all these items without spending efforts of R&D, and these are the software tools that I mentioned. The Eolytics and the Watcor-X tools. It's the only commercially available SDB software. It's been developed over 15 years of continuous development, not only internal but also with interaction with the users, such as Commanders Waterson from the Australian Navy and others. And it has been proven, it has been demonstrated to be very effective through applications throughout the world. And this is in part due to the excellence of the physics-based concepts, the actual mathematical tools that we use for development of the software. It's standalone, and we feel very proud of the software, and we feel there's a lot of use for it throughout the world. And to demonstrate the software, I will now turn it over to my colleague, Christian Boedinger. Christian is a remote sensing specialist. He has advanced knowledge and experience in satellite imagery applications, data analysis, and workflow automation. And at EOMAP, he's worked as an SDB analyst within a number of commercial and research and development projects around the globe. He's supported by a team of physicists and IT experts, and he's responsible for the implementation, development, and supervision of the Watcor-X software. So in that role, he's provided training on Watcor-X globally and serves as the main point of contact for technical and other related matters. He holds a master's degree from geography from the University of Tübingen. So with that, I will now pass it over to you, Christian.
So thank you, Edward. And I will just start my presentation. So, hi everybody. So I will now present you a short tour to our, through our Watcor-X software, which is a physics-based SDB processing software, and the only one that is on the market right now. So, first of all, we had a couple of objectives, core objectives for developing Watcor-X. First of all, we wanted to create a ready-to-use software that is working independent from any kind of survey data. And to do so, we implemented a fully physics-based workflow into the system that grants a high level of automation and requires only a minimum of user input to work with the data. So, and let's start right away. So in the following, as I've seen like a question in the chat before, asking if we need to purchase data to process SDB. So the answer here is no, you don't. I will use here open source and freely available data from the Sentinel-2 satellite, from the ESA, which has 10-meter resolution. And I will use this data as is, so in the raw form that everybody of you can just download as is. So let's start with just ingesting the data into the system and specifying where to save the results to. And now we set up the workflow, and we can have now a couple of configuration options. For example, we can decide whether we want to process on the graphics card or use multiple CPUs. And now you can also do some adjustments and configurations to the workflow in advance, but you're not required to. So you can also do this later on, or you can just process as is. And then the image will be loaded into the image viewer. So the scene here is a location from the Virgin Islands. And you can now draw your AOI, your region of interest, on the map canvas, or load your already existing AOI from your desktop. So I will load one AOI from my system into the map canvas, and I quickly zoom in a little to have a better overview. And now let's enhance the contrast to have a better view on where we find optically deep water areas. So areas which are optically deep. And the last thing we do is drawing some polygons over these areas for a reference. And now we are ready to start a process, and everything else is done automatically. The system will run through, and there's no further user interaction required so far until you can finally have a look onto the results and inspect what is the outcome of the software. So let's have a quick look on the results, which are stored in your specified results folder. And you have here a RGB display of the satellite image and a color-coded GeoTIFF of the SDB, and also some other files. But what you get out of the system is up to you, so it's configurable. These are standard files that can be used in any kind of GIS system and also in any kind of other software like Chimera. As we heard before, QA/QC processes are quite important to assess the accuracy of SDB processes. But if you have validation data available, or for example also the Atlas data, you can compare them with the SDB, but you're not required to. So this is an optional step, and I will just use in the following. Of course, you can also make a title correction if you experience you have a title difference between the satellite image taken time and the validation source. And then I will import a validation LiDAR set from the NOAA and finally trigger the validation. And as we see here, that's the comparison between the SDB as processed as is without any further configuration compared to the LiDAR data set. So 10-meter resolution SDB compared to the high resolution LiDAR data. And we see we have already a pretty good fit to the one-to-one line between those both. 78% are within the standard boundaries of tolerance boundaries of 1 meter and 10% of water depth. But in the following, we will see if we can further improve the results by a couple of other options. So let's first take a deeper look into the data. So Watcor-X also provides the possibilities to for experts to take deeper look on the data, to view intermediate products, and to configure different steps. So as you see here on the right side of the GUI, the workflow control panel, every kind of step that is blue marked has already run through successfully. And we also have a ample system supplied here, indicating in different colors where the user might potentially pay attention to. So if I have a look here, I see that there's a warning triggered at the atmospheric step, indicating that I have a high aerosol concentration here. And I can visualize this in the software directly and see what the AOT concentration, so the concentration of aerosol optical thickness that was calculated per pixel by the software is like. So we have values of 0.55 here, which is quite high aerosol concentration, indicating that there's heavy atmospheric impact. So in this case, where I have this environmental limitation, it might be interesting to also have a look onto other data sets. And the same could be true if you have partial turbidity or a lot of boats in the scene. And to deal with this problem, we have integrated a multi-image processing into the software that is using different kind of scenes and process them all together to minimize this environmental impacts and thereby increase the reliability on the results. So as you know, or you might know, it can be a quite time-consuming process to look through all the data and filter out which satellite scenes might be useful for processing. And to do so, as already was presented by Edward, we have developed this Aeolytic Swift tool that might support you in your decision. So let's quickly have a look into how to set up a multi-image process. And you will see this is quite an easy thing to do if the process has already finished. So the process of the single scenes. So I will just switch to the multi-processing here and add some other readily processed scenes and import them into the Watcor-X software. I can now correct for the tidal differences between those scenes to bring them all on the same level. And if I've done so, the rest is quite straightforward. I just can apply those configurations and start the whole process. And now, as before, everything will run through automatically, and I just need to wait till the process has finished. If it's finished, I can validate once again to make sure that I have an improvement and that taking into account multiple images has increased my results. So let's repeat the steps we did before for the single scene and load into the LiDAR validation set for comparison with the SDB. And if we do so, we see that we have a pretty good fit between the Watcor-X SDB and the LiDAR depth, which is 93% between a tolerance bound of 1 meter and 10% of water depth, which is also an increasement of 15% towards the single scene results. So in this case, we really got a quite huge improvement by taking into account the information from different kind of scenes. So as a short wrap up on this topic, you've seen Watcor-X is a ready-to-use software that requires a minimum of user input and has a high level of automation, being fully independent from surveying methods. You can just use them for validation purposes if you like, due to its physics-based background. And it also has the possibilities to process multiple images to increase the reliability on the results. But it might be as well that you are not after a fully physics-based workflow because you already have a pretty good coverage on your data, so your survey data. So it might be handy for you to have something to fill those gaps. And here we also have a solution right at hand. It's called Analytics SDB, and it's an online tool that is working fully independent from any kind of hard or software. So you can even use it on your cell phone and trigger SDB processes on your cell phone to get the full coverage bathymetry. So this was just a short excursion. Of course, we have limited time options here, but if you want to learn more about this, you can contact me via email directly, or contact us via the contact formula on the SDB Day homepage. And you can also request a training or a discussion on more detailed questions on that site. So thank you for your attention, and I hope you can enjoy the rest of the SDB Day.
Thank you, Christian, for that excellent presentation. I see we've had quite a number of questions within the chat, which I see Knut has been maintaining. If there are any more questions, please text it in the chat and we'll address it. But while we're waiting for that, let me go through some of the questions that were asked during Christian's presentation. So one question, are tide level corrections done with tide gauge or global tide models? The answer is both. You know, if there is a site-specific tide gauge, we'll use that, and if there's not, we will use the tidal predictions from the tidal global models. And the question, does the method work in estuaries and deltas where we have turbid waters? And the answer is, if this turbidity is seasonal and all year round, SDB, as well as airborne LiDAR, cannot produce depth. However, the beauty of the satellite technologies, we have the ability to go back in time. So we can go back and maybe find an image that is clearer and less turbid, and we can process data from there. And that's one of the advantages of the SDB over you know, other types of methods. And before we can do an analysis of satellite imagery for SDB suitability, would we have to purchase it? And my colleague Knut has answered that already. At this stage, EOLETIC SWIFT made for satellite data is free and open data policy. No costs will apply to the data. But in the 4S project, we'll bring it to the commercial data. You will not have to pay for the search, for the final access to the data. There will be costs associated with that. And what is the cost of the desktop-based software? The cost, please email us, please register your interest. And the Knut has provided a link there. It's on the SDB.org website, and you can we'll provide further insight into pricing, model and pricing and training and so on. see we have 2 new messages. I won't go through all of these due to time constraints. But maybe Knut can answer some of the more technical ones. So does Eolithic Swift grade images based on sunglint as well? Is sunglint important consideration for selecting best images for the SDB workflow? And Knut, I don't know if you'd like to expand upon that.
I'm writing books here, so don't worry.
Let's make it a little easier on you.
So yes, sunglint is also considered here in this classification process. So and also I invite, like, if you have interest in that and want to see how it works in your specific area or site, yeah, just go to this web link, which I will actually right now put into the chat again. So just contact us here and we can set aside a bilateral meeting. And I think then it's more targeted and more easier also for you to understand and for us and you to ask questions and respond to them.
Well, there was a number of questions that I see Knut has answered. I think most, or if not all of them, in the chat. But Knut, if there's anything that you would like to expand, verbally, based on the questions that have been asked, that you can think of.
Sorry. There's nothing specific. As said, I would encourage you really, if you see interest, simply let us know in this contact form or later on, and we will simply set aside these bilateral discussions, let's say. And I think we are a bit in a hurry to make the time, so I think we are probably somehow exactly in time at the moment, but I believe it's best actually to hand over to Kathy, because there's the next session is still actually pretty interesting, I think, for those which work with SDB data. So Edward, if you don't.
Yes, absolutely. Well, Katie, I'll now pass it on to you for the last session. It's SDB standards and best practice for adopting SDB. Katie?
All right, thank you very much, Edward. So our presentation for this session is being done by Sophie Loyer, who is with the French Hydrographic Office. She's going to be presenting on behalf of work that she has done with her 2 co-authors, Yvonne Lubac and Christophe Vrignaud. And Sophie has been a project manager in the Department of Research and Development since 2017, with a focus on SDB and decision support tools. Before that, she was in charge of acoustic multibeam data processing, and earlier in her career, she was a coastal and marine ecosystem research scientist. So, Sophie, please.
Okay. I tried to share my screen, but okay. Do you see my screen, everybody?
Yes.
Okay, nice, thank you. Hi, everyone. Yes, I'm working in the French Hydrographic Service, and I'm the speaker for the moment, but 2 other of my colleagues are associated to this presentation, Yvonne Lubac and Christophe Vrignaud. And thus we want to present you our expected use cases from an hydrographic point of view with regards to the latest technological progress. Why we have expectation? It's because thanks to the new generation of satellites and latest SDB breakthroughs, there has been a renewed interest in the use of optical satellite data. And in this context, the French Hydrographic Office has expressed its interest in this technique, and it has reinforced its efforts to improve the product's reliability. And we want just to present you our expected use cases and the challenges faced with them, dealing mainly with the need to manage the uncertainties of the SDB product. One of the main use cases we have, and it's probably the most common use case, it deals about the use of SDB as a reconnaissance tool. And as far for SHOM, these use cases mainly deals with the support to the general bathymetric knowledge in remote areas. Because today we are faced with a strong need in terms of bathymetric knowledge coming from a diversity of community, which is difficult to satisfy with the usual systems such as multibeam. And with a responsibility area of about 11 million square kilometers, many of these areas are far away and are with a limited access to conventional systems. And clearly, our interest in SDB is due to the fact that we have to mitigate the lack of in-situ data. But be aware that because we have a lack of in-situ data, it's already a challenge because it strongly limits the choice of SDB method that we can use. And most of the time, an empirical method is difficult to use because we have any data. Another expecting use cases is to increase the performances of seastate models by providing them a more efficient and complete bathymetry in very shallow waters. And because satellite images can cover large areas, can include sea-land interface and can have high revisiting capabilities, we think that SDB can clearly help us to improve the data coverage along the coast. And keep in mind that these reconnaissance use cases are commonly accepted, mainly because the constraints in terms of vertical requirements are quite low. These second use cases correspond more to a specific need for a hydrographic service, as it relates to the planification of hydrographic survey. With a portfolio of about 900 charts, we have to collect data in all areas placed under the French maritime charting responsibility. And this job is carried out inside an annual national hydrography program, which determines where to survey and when. And this planning is updated in an annual process in order to follow the progress of this survey project and the state of knowledge. This planning job takes into account the need expressed by as many sea users as possible, the traffic density also, and the need of improvements for nautical charts. This is clearly a big task, as it, of course, also needs to include possible seafloor changes over large and remote areas. Thus, to assess where the seafloor is changing, it will be useful to use any possible source of information, and SDB is one of them, of course. Nevertheless, compared to the previous case, it becomes more important to pay attention to the vertical uncertainties of the product if you want to be able to determine the order of magnitude of the detection of changes that can be found with this SDB technology. And now we arrive to a more complicated use cases from the French point of view. It concerns the use of SDB for cartographic purposes. Here in the screen, you can see a nautical chart that illustrates the portrayal of an area covered with SDB measurements. And it is a portrayal actually to date adopted by SHOM. Because faced to the low accuracy of SDB product from our point of view, compared to other conventional systems, and above all, due to the difficulty in estimating the uncertainties, for our cartographers, SDB is currently considered as a non-classified information, and therefore considered as an unsurveyed area. Therefore, when we have SDB information, plot on the chart chart is only charted with a colored background depicting only contour depth range, and only soundings coming from conventional survey methods like multibeam or LiDAR are plotted on the chart. And to date, for us, this use is limited to few Pacific atolls. More words about this need to use international norms. We want to bring your attention to the new version of the S44 publication released by the IHO last September. These international norms provide us the minimum specification for hydrographic surveys dedicated to the safety of navigation, with a well-known order defining the different levels of surveys. And in previous edition, with only these orders, as you can see in the table on the screen, there was no room for surveys dedicated to topics other than safety of navigation, like geophysics, oil and gas, dredging, inspection of structure, and so on, because these well-known orders are very selective. Thus, as you can understand, this new edition has a lot of improvements from this point of view. Of course, this new edition is still designed for safety of navigation, but with the new matrix of specification, it sets the stage for other applications on this other type of surveys. And these tables include the criteria used before, but now it offers different value for each of them, and all of this value can be used to specify the customer needs and thus to identify the appropriate acquisition system to answer with the right needs, or to qualify a survey a posteriori. Clearly, the aim of this new matrix of specification is to give more flexibility, and it has been designed to meet a maximum of needs. That was an aspect completely absent in previous version of the S44. And this new table is now no more based on a selective technology such as sonar system. And with this possibility to include new needs, we can expect to apply it to other data types, such as satellite data. For an example, and for illustration, we did the exercise on an SDB survey carried out on a well-known test area with a small geographical coverage and for which we have in situ data. This product that you can see at the screen is based on a pure remote SDB analysis without using any in situ data for on-site calibration or training model. But of course, if the SDB is performed without using in situ data, we have been able to perform the qualification thanks to our reference bathymetric dataset. And in accordance with the reference data used and the gap with them, we estimate that this SDB can be qualified according to the following criteria, as displayed in this table with the red circle. For each criteria, like depth, we have estimated the uncertainties of the product, and we have selected the corresponding values in the table. Just to note that for the SDB survey, the vertical uncertainties associated, all the uncertainties put in this table are associated to 95% of data. And for the vertical uncertainties, it has been estimated to 4 meters, but we have to fix the value to the more close value found in the table with the safety of navigation concept. And for that, it underestimates a little bit the accuracy. Here, there is always the same information. It's just another way for illustrating the qualification of our SDB by plotting some criteria of the new S44 on a diagram in regards to the value selected in the table. And this illustration enables us to compare this assessment of SDB qualification to order true with a depth reference at 15 meters. And what we can notice is that except for vertical uncertainty, the SDB offers many assets and is clearly complementary to order 2. And to complete this topic in a similar way to S44, be aware that the cartographers have also to be compliant with standards, illustrating the quality of data given in the nautical chart. And the information depicted are compiled in a chart. The information depicted are compiled from data coming from multiple sources on different systems. And each of them provide a classified information merged by the cartographers through the CATSOC classification in order to provide quality information on data displayed on the chart. Of course, these estimations are based on the S44 qualification of the survey, data used to create the chart, and thus it requires to make a correspondence between S44 and the CATSOC, which is not intuitive, but possible. And that means that for SDB, even if we are able to specify it with the new S44 matrix, its integration into the CATSOC classification is not yet certified with the correspondence currently known, except if the survey meets the previous well-known order. Thus, we have to do a new job with the new S44 classification in order to adapt the correspondence with the CATSOC classification.
3 minutes, Sophie.
Okay, it's a fact. In summary, whether with S44 or with S57 CATSOC, we have to define important values related to the uncertainties for horizontal measurements, for depth measurements, feature detection capability, and seafloor coverage. And across our different experiences with SDB, it appears that 2 of them are challenging for the SDB technique. And if SDB can be processed without the use of in situ bathymetric data, the lack of in situ data, it becomes a real problem for it's a real problem for the estimation of vertical accuracy and capacity of feature detection. Nevertheless, they probably are the key points to go deeper with the use of SDB for an hydrographic surveys, at least from our point of view. And to finish, we are convinced that SDB offers an interesting potential for feature detection and for the retrieval of mean depths. But now, our main question is, in what extent can we improve the assessment of uncertainties? We know that it's a complex issue because many factors are involved, like the uncertainty of the reflectance measurements, the quality of atmospheric correction and of correction of other environmental effects. And if we go inside the model inversion itself, the parametrization of the seafloor reflectance is crucial, but this parametrization has some limit to reproduce the seafloor complexity. And at last but not least, it to be well fitted during the process. And it can explain some discrepancies in the vertical uncertainties inside the same area. Therefore, our question is, how far can the SDB producers master the uncertainties? We have a look on some results of uncertainties, calculation, computing during the process, but they are not always realistic, and there is a great variability in the efficiency of the solution. Our question is, can we use the multi-images processing to make results more reliable and also to estimate variability in the depth retrieval, for example, to assess the impact of out-of-control processes? And we have also seen an interesting presentation addressing the turbidity and sand selection. It's also a key point for future improvements, especially if we look at multi-image processing. And according to this ambition to do multi-image processing, we think that the question of measurement stability and sensor calibration also needs to be analyzed in detail. Thank you.
Thank you, Sophie, very much for a very interesting presentation, and certainly a number of implications of challenges that still remain to be addressed. So I would like to take a few moments to see if there are any questions for Sophie, and if there are any, please, can you put them in the chat? And just a reminder to those speakers to turn on their cameras when they are responding. So I'm just checking. I'm not seeing any questions so far in the chat for Sophie. I'll just give another moment. All right, well, it seems that there are no follow-up questions to Sophie's presentation. Thank you again. So as we go into the conclusion of the conference, certainly all of the presenters have identified a number of challenges, tremendous potential, and clearly the necessity for moving forward on a number of fronts as SDB continues to be utilized and applied. So in order to stimulate some thinking and some input on perhaps some next steps that could come out of an event like this, I'd like to turn it back to Knut Hartmann, who's going to introduce some polls which have been designed to collect your feedback.
Thank you, Katie. Yes, so we have some polls which we've created just to, yes, exactly as Katie said, just to get the discussion a bit going, to get your thoughts. Before actually doing this, I would ask all the panelists just to turn on the camera so that all of you can be seen. So I'll just wait a couple of seconds so that I probably have to allow Thomas again. All right. Thank you. So I think here we are. All right. So we have 4 polls. I will start them one after the other, and you will also be able to see the results. The polls are anonymous, so you can honestly answer. And the polls will appear as pop-ups. The panelists will not be able actually to use a poll, so don't worry. It's just the participants of the talk which are able. So I start the poll right now. So you should see a pop-up, and the question is, do you actually see a need for standards or perhaps best practice for SDB? So we thought of 4 answers. So one is yes, it's mandatory. If I don't have that, I will not use SDB. The other is yes, but it will not stop me. Or no, it doesn't affect my work at all. How I use SDB. Or of course you can say I don't know. So I'm just giving you a couple of seconds. Have a think about. I see about 50% of the people have used the poll already.
Knut, I'm not able to turn on my video.
Oh. Oh yeah, sorry. All right. So I see people are still using the poll, so I'll just wait a couple of seconds and close it now. So I share the results. I think they should also pop up actually. So what we see here in the polls is that more than 90% have replied with the answer 1 or 2, which simply means yes, we see a demand in standards and best practice for SDB. So for 13%, it's mandatory. 80% said, yeah, it's important, but it doesn't stop me at the moment. And so there are only very little actually which say it doesn't affect my work. So which in return means there's a high demand, obviously, for the work which Sophie and her colleagues are doing, the colleagues from the IHO are doing in the working group, and of course the experts doing around the globe. So I think this is a pretty interesting. So from the panelists, anyone want to comment on this? Don't worry, I have other polls. So Thomas, go ahead.
It's just a comment that came up when again realizing what Sophie showed with the new S44 standard. And the question is, of course, how we can grasp from this, for example, more systematically measure than now, from now on, for example, within this new standard. What do we achieve at the actual best practices or at the different practices that we actually have? Then for different reasons, because we see just one view comparison doesn't make any sense because the variety is just too high. That means we need a larger approach to measure this and also a larger approach to further push this, because what we see both things, there's a high variety, but there's also a development line. So that's the question then again to the hydrograph, to the offices, maybe research institutes, IHO, how to structure this path.
For the French hydrographic services, we pursue the comparison of different SDB products on many geographical areas in order to improve the technique and to assess how SDB can be qualified on a more general sense. And of course, we also have a lot of expectation according to the estimation of uncertainties. We do the qualification only when we have in situ data, and we hope that you are able to improve the uncertainties estimation because they are at the base of the process qualification. It's clearly the base for us, but because we are an hydrographic service and we have some responsibility, it's not so simple for us to use SDB if we cannot be confident on the product, but confident everywhere. But we think that we have difficulty to respond to all the answer we have about bathymetric data, and clearly we need to use other kind of data like SDB. And we have a big expectation of the improvements you can have.
Yeah. So, which actually, Sophie, I mean, it's obvious that this kind of improvement needs iteration. So it needs iteration between the expert, the ones doing the algorithms, the ones doing the software and stuff like that. Which directly leads me to my next poll, which I want to put out, and I'm a bit afraid, Sophie, that you are not allowed to vote for that, but feel welcome. So the question is, are you actually interested to support work toward a best practice guideline and standards for SDB? This does not exist at the moment, to be honest. So the question is, we have the assumption that it needs actually multiple teams, multiple understanding from different applications to make this going and make it reality in practice. So the question to you is, do you see that you can actually participate in this kind of group? Obviously, there's no agenda right now, but this can actually be an outcome of this session. So people are still voting, so I'm just waiting a bit. Okay, so I'll close the poll right now and share the results. So about half of the people say that yes, I have general interest to join this kind of group, and about 30% are not yet sure. So actually for me, that is astonishing. I did not expect really to have more than half of the participants being interested to that. So let's say on my best guess, I would thought that perhaps 20% or so would be interested to that. But this is astonishing, and we saw in the first poll that there is a high demand for this kind of standards. So what we would like to do, if you like, also as a take-home message for and output of this session, is we obviously want to establish this kind of group, a group which comes together without commitments and discuss different topics on these technologies. So just as a starting point, actually, we have again defined this kind of contact formula at the SDB Day page. It's sent by the chat formula right now. So if you are one of this 54% which has interest in that, I would ask you simply to register in there. As said, it will not be a commitment or so. So I think in the next weeks following the event which we have in Asia and Oceania, we will have a first agenda of this kind of working group, let's say, and we'll provide you with the first information and ideas of how we can make this going. But really consider it that it obviously requires exchange and contribution at the end a bit. So any of the speakers again wish to comment on that poll or the idea of this kind of best practice working group?
Maybe from my side, I think it's very important for us as in the industry as well to have a clear understanding and guideline if we are using that. Also for our clients in the cable route business, I think they rely on our data sets, and if they approach the landing site with their cable laid whistle, it must be in any case classified or clear what we are providing them. So that's very important for us, and I think we are also happy to assist this process and yeah, do the best to have these standards. And I think Sophie, your presentation was very interesting, and a lot of things could be discussed further there.
Of course, we are also interested in participate to the process.
And I'll note, as I'm in an agency that also does charting, standards are critical in order to establish the charts, but I assume that comes back into other communities. So yeah, it's we get lots of questions internally on establishing standards as far as our charting group goes and trying to implement this. Same, just like you, Sophie. So.
Perfect. Thanks for the good comments. Any further on that?
I am noticing, Newt, in the chat that David Wyatt from the IHO Secretariat is saying, hoping that representatives from the SDB sector will participate in the newly established hydrographic surveys working group, which evolved out of the team that developed the new edition of S44.
Yes.
So perhaps some follow-up communication with the IHO would be appropriate.
Yes. Sophie, I think, correct me, but your colleague has been the chair of this working group,
yes.
Or is still the chair of this
yes.
working group? And
yes, Christophe Vrignaud is directly implicated in this working group.
Yes, yes. So this is definitely for the hydrographic world, I think, a major step. I mean, there are probably other applications where hydrographic standards might not be needed, so there might be more towards best practice guides. So this is something which I think we have to address. Yeah. Okay, so I'll have actually a very simple one. So here it comes. do you actually feel that you have now sufficient information about SDB technology to apply it for your projects, for your tasks? Would you see that's okay, I understand it, or no, I'm not sure if it works for my specific project or application or location? Do you feel like you're comfortable with the information which you have so far? All right, so I'll close the poll and now actually. So it's like 1/3 says no, I don't feel comfortable enough, and 2/3 say yeah, I probably have enough information, which is again a bit of surprise for me. So I thought there were more question marks actually on this technology, but I consider this as a good outcome for the sessions which we've done today. But I'm also sure that questions will arise on specific application or for specific sites as well. Again, I ask the question to the conference, anything to comment on that? If not, I will just go to the next one. And the last question which we have prepared is actually a multiple choice one. And the question is, where would you see the future development? Where do you see the biggest need? So is it like the increased level of the level of the detail? So would you like to see more smaller obstructions? So would you like to have higher spatial resolution? Or would you like to improve the vertical accuracies and thus data quality? Or would you like to quantify, so to understand these uncertainties? Would you prefer a software actually to do it yourself? Or do you see the need in standards and best practice? Again, you have the option to do multiple choices. I can see it live on screen, so it's a hot race.
Yeah.
Okay. So I think, oh no, people are still voting. Okay, I'll close it now and no, not now. Close it now and share the results with you. So it actually got obvious that 70% of you see the highest demand for improvement in improving the vertical accuracies, but also quantifying what those, so error budgets, if you like, of the SDB. So like 70% of all of you say that is a really high demand. Then the rest is more or less similar. You see a similar demand for standards, creating tools, software tools, but also you see a demand, or at least 40% see a demand to increase a spatial resolution level of detail, which is, I think, in line, very much in line with this session which we just had, so that we see a gap in this kind of standards data quality to, first of all, to bring them into practice actually for SDB. And yes, it's also in line with the developments of SDB, I think, because all the journey of SDB along the almost decades now, it always, well, at the end resulted in better uncertainties and better spatial resolutions if we just see the history of how it was like 10 or 20 years ago. And I believe this journey continues, and these are exactly the points which drives this journey, I think. So speakers, up to you again. Yeah, it's late in Europe. I have to apologize.
Well, still early here, so I'll respond. I do see that as the biggest question we all need to answer, is to clearly establish accuracy and uncertainty. And what is the uncertainty, not only across a project, but within a project, because it will vary. There are conditions that cause all the methods to vary from pixel to pixel. And we really need to capture that, because that's understanding. So that's a challenge for all of us to get this figured out. And that will increase confidence overall. So I think that's the task we need to go away with. So I'm still awake. So we got a full day left here. Right.
Richard, you as one of the early adopters and developers of SDB, how would you see like the where's SDB? Like if you see a roadmap, is it like just started, or are we at the finish line? Where do you see the SDB technology? I will ask the same then to Thomas and see.
We're in the middle here. It is being put to use now, and as I go back as early adopter, there was a reaction 10 years ago of why do you need satellite bathymetry? Now there's a huge recognition of the need for this because of remote areas, because of rapid response, and it is working. People are putting it to use, but I think we're right. I think that's the middle point is captured on making people confident in the products they're getting. And that I think will really push it over on this. Also, tying it in with the IHO more tightly, so it's very clear from an IHO perspective exactly how it gets incorporated in. Those I think will push us over the finish line, so it will then become a routine part of the whole system rather than a add-on, which is kind of where we are now. It's being used, but it's more of an add-on rather than routine. Would kind of capture that. But we're close. We're definitely on the right track, and I think we have a couple more years here, and within a few years we will be there.
Thank you, Richard. Thomas, would you agree? Do you see any difference in your opinion?
No, it's really the same. From the technology involvement, I see it in the middle. There's still lots of things to do, lots of to further integrate and improve. So there is room and hope for Sophie, I think. But there are other elements. So as you mentioned, it is at the moment it's in the race still. So there's increased phase of, but not only of the technology, of the awareness. And when I look back to the last years, I think it was maybe 5 years ago when Robert Watt took it to the IHO level, then of course there's a lot of not so much, well, not at all confidence, and that is a level method to use because of the thing. So there was already a great development, but I would say from this perspective, so from the awareness to make a working group right now, it's just in the middle and it's the beginning to systemize this, I would say.
Yes, from a user point of view, we also think that a lot of improvements have been done, and now it's clearly time to go deeper in the uncertainties, but we are close to have a good result because many good things are on the way, and it's a good way.
Thank you. All right. So the chance is also again to the participants to use the chat if there are any questions. The time is a bit running short, but we will be able to check your chat inputs if you have any. All right. So I'm just waiting a couple of seconds again. And out of whatever reason, we are right in time. So we made it in 3 hours. I didn't expect it. So thanks to Katie really for making the moderator and being tight in time here. That's very much appreciated. Thanks for all the speakers, for your participation, for your preparation. Thanks for the people here also at EOMAP, which made it going. With these words, I actually like to wrap up and close this third international conference on SDB for the focus region here, Europe and US and Caribbean. So I think, first of all, I think from the audience, simply it has been a good success. So you have not seen it, but we have 120 people participating in this event. which is actually a huge number if you consider this kind of still somehow small group of which actually use this technology. So which shows me actually that together with the presentation which we have heard here today, we have a vital and really progressing technology, technology which is really, let's say, living, it's developing. We see the different kinds of technologies, even methods which are being applied. Not only this, we have beautiful or great use cases here from defense, actually, starting with Commander Chris Waterson. We had seen examples for charting, for planning, or even for coastal engineering tasks. So those are all use cases where SDB already profits, and obviously with further improvement can still provide further benefits. Obviously, there's a lot of thing which is still in the agenda. So we are in the middle of the race, let's say. So there are, and that is in line with what you have inserted in your polls. So you see a demand for further improvement and understanding on uncertainties. But in addition, well, let's say it doesn't come for free. It requires a bit of interaction and discussion. And for that purpose, I believe it's a good approach to really think of this kind of joint working group towards standards is a big word, but let's consider it first at all as guidelines of what's the best to do, and with developing but also verifying SDB things. So we have this kickstart here for this kind of group. I please remind and ask you to sign in this group. You saw the contact details in the chat, but it's also at the sdbday.org page at the contact panel. So just go there, insert your registration. We will await the other event, which will be held in 2 weeks' time for the Asia and Australian time zone. We will ask the same question, and I'm sure we'll get other people to join this group as well. And then actually we have a unique opportunity to fill data gaps in space and time with this technology. Actually an opportunity which is unique to this technology. And yeah, it's a great journey, and it's a pleasure to continue this. And with these words, I really wish to thank every speaker, Kathy in special, really for moderating this, and the participants for spending the last 3 hours with us. The video will be recorded and shared after the Asia event. Thank you very much.
Thank you, Knut, and everybody. Enjoy the evening while here in Europe, at least, and the day in US and Caribbean.
Good evening, everybody.
Bye-bye.
Thank you, Knut.
Bye, thank you.
Thanks. Thanks very much for allowing us to participate. And bye-bye.
Bye-bye.
Yeah, thank you again. Hope I'll actually see you in person.
Same. Thanks.
Same. Let's hope so much.
Great.
Right. Goodbye, everyone. Thank you.
Bye.
Bye-bye.